So thank you. First of all, let me thank you, Jean-Guy, for this very warm welcome here at KIAS and Seoul more generally. It's really a pleasure to be here. And I would like to talk about Kleinian singularities, but I would like to start with Felix Klein, because Hiraku talked about fields and fields medals. So let me go a little bit further back in time and start with Felix Klein. So he has been professor in Erlangen and other places, but maybe the first moment which is interesting for us when he came to Göttingen. And so this was in 1886. And Göttingen, of course, is not Berlin and a small place, but was famous because of Carl Friedrich Gauss and Bernhard Riemann. But in 1886, it seemed to be a little bit a moment where it needed to be renewed. And so some person who is quite famous at that time is Friedrich Althoff. So he was a politician, and from the Prussian Ministry of Culture, because it's the Ministry of Culture who's running the universities in Germany, at least in Prussia, that was the moment. And so he hired Klein to come to Göttingen, and Göttingen dramatically changed after this. And Friedrich Althoff was the main support of Felix Klein. So whenever Felix Klein wanted to realize something, he just called him. But I mean, calling in the sense of writing him a letter. So maybe for us, the most important thing at that time was in 1893, he went to Chicago. So Chicago is the pre-ICM. So it's the one where Felix Klein probably had the idea of getting International Congress of Mathematics, of mathematicians on a more larger scale. So in Chicago, there was the Columbian Mayfair at that moment. And so Chicago math department was only 2 years old, so very young. And so they made this Congress. And so there were, if you look at the proceedings, you have the impression that there were many mathematicians, but in reality, only 4 came from abroad. And Felix Klein was one of them, and he was the imperial representative. This is because Prussia and Germany at that time was an empire. And, so in 95, he hires, with the support of Friedrich Althoff, David Hilbert. David Hilbert came from Königsberg. Königsberg is now in Russia, it's part of Russia, but at that time it was East Prussia. And so David Hilbert did his PhD with Friedrich von Linnemann. So you know him because he proved that P is transcendent, first person to prove that. And the academic grandfather of David Hilbert is Felix Klein, because Felix Klein's student was this von Lindemann. And so another interesting fact for 1895 was that the first female PhD in Göttingen, among the first at least in mathematics for sure, has been done under by Grace Chisholm. From her advisor was Klein. At that moment, she's British, so she was not allowed to do her PhD in Cambridge, where she came from. And she had to go to Göttingen, and even in Göttingen was not allowed to make a PhD, but Klein somehow managed to get a special authorization. So I've put her, she married later Young, because you know Young, because of the tableau, and she's very famous for her work also, and also the work she did with her husband later. First ICM, 1897. So the LOC, well, two main figures is Adolf Hurwitz and Hermann Minkowski. Hurwitz is a student of Klein, and Minkowski is an academic brother of Hilbert. So he also comes from Königsberg, had the same advisor as Hilbert, but he was in Zurich, as Hurwitz was, and the first ICM was organized by them. Second one was organized by Poincaré and Picard. Poincaré was already in Zurich very present. He was among the committee who decided about the scientific organization of the ICM in Zurich. And at that conference in 1897, Hilbert was not present. And it also happened that in 1897, the first ICM had been boycotted. So had been boycotted by the Berlin Mathematical School, because they, especially Kronecker, Kummer, and Weierstrass, found that the mathematics of Göttingen was a little bit, maybe not, they would like to see mathematics, especially the work of Hilbert and others. And so Minkowski convinced Hilbert for the 1900 conference to give a list of problems. So the famous 23 problems. So the idea came from Hermann Minkowski, and we remember the ICM in Paris for this. I just skip to Rome. In between was the conference in Heidelberg, organized by Volterra and Guido Castelnuovo. Why? Because ICMAI has been founded in Rome. So the International Commission on Mathematical Instruction, and Felix Klein is its first president. So Felix Klein got very much interested in mathematical education when he became older. And so ICMAI existed before IMU existed. In 1915, Klein and Hilbert invite Emmy Noether to Göttingen. Emmy Noether is not allowed to get a position, because at that time, women were not allowed to have a professorship. But after World War I, in 1919, rules change, and she's hired. Next year is 1920. Jiraku has explained to us that IMU has been founded. First ICM after World War I was in Strasbourg, 1920, as I said, and Germany was excluded. So especially Felix Klein and David Hilbert were not allowed to come to the 1920 Congress. And so one of the person who was in Poincaré was already dead. He died in 1912. And Picard was very instrumental, together with the first president of IMU, de la Vallée-Poisson, to exclude Germany from the ICMs. We've heard it. 1924, we are in Toronto. 1928 in Bologna. And in Bologna, David Hilbert came back, and he said, für die Mathematik ist die ganze Welt ein einziges Land. For mathematics, the world is only one country. He's famous for this quote at the gala dinner. And another quote he made that evening was that mathematics don't know nothing about races. And so I would like to start the story with Kleinian singularities. So explain a little bit what they are, going slowly and going a little bit faster later. So it comes from, find most of it in the book by Felix Klein, Vorlesung über das Ikosaeder und die Auflösung der Gleichung vom 5. Grad, 84. And let me start with an example. So what does he look at? He looks at finite subgroups of SL2 of C. So then if you take such a subgroup, it, of course, acts on C2 just by the action of SL2 of C. You can look, if you like, at the cyclic subgroup of SL2 of C, which is a finite subgroup if you take psi to be a primitive nth root of unity. And so the action is, everything is very explicit. And then you take the orbit space. So we have seen this yesterday in John Kuhn's talk, but we do it in the algebraic way. So because Paolo, he doesn't like stabilizers at 0, and so stabilizer group is huge, so there's no quotient in the way one would like to see it if you look from a more differential point of view, but in algebraic geometry, it's actually simple to construct the quotient, but you have to allow yourself to have singularities. So the way it is done is you look at the action on the functions over C2. So the coordinate ring of C2 is just polynomials in 2 variables. I've called them big U and big V. And then the group G acts just by seeing the polynomial as a function. And what we do then is to look for invariant polynomials and relations between invariant polynomials. Here again, I'm going back to the talk yesterday. We were talking about invariants and relations between invariants. So we can look at an example, the one we already looked at, the cyclic group. So if I look at 3 new functions that I call x, y, and z, u times u to the power n and v to the power n, and the product u times v, these are invariant functions under the action of G. And then there's a trivial relation between those functions, namely x times y is equal to z to the power n. And then it turns out, this is shown by Klein, that if you look at the ring of all invariant functions, that's it. There are 3 invariant functions and 1 relation between the functions. And the relation is the one it is. And it turns out that the quotient identifies to a hypersurface in C3, so surface. If you define by one equation, today we would say we look at spec of the invariant functions, and we have the inclusion of the invariant function into all functions, and the quotient map is just the map from C2 to xg defined on the level of specs. And let's have a look at it. So let's draw it. So it's z squared minus x times y equal to 0 for n equal to 2. And one can have a look at the first singularities we see. So there is something which is a little bit strange, but we'll see it in a second why it is like that. So the first and the third look similar, and the second and the fourth look similar. Please be careful with the fact I'm talking about complex, but I look for real pictures of them, so it takes a little bit of, one has to be careful about how you see these, how you represent them in the real world, but that's a very typical representation. And so let's look at another one. So that was Cn. Of course, there's another subgroup you know very well. This is the Quaternion group of order 8, or other people, as I prefer to call them, the binary diedral group BD2. So it's just generated by these 2 matrices in SL2 of C that are written there. And so if you look at this group of order 8, here again, one would like to look at the quotient. So get invariant polynomials and look at the relation you find. So here you get, again, 3 invariant polynomials. It's easy to find them. You just look at alpha and beta. And then the relation is also easy. And then you know that the invariant ring, there's something you definitely have to show, is given by that. And if you go to the next slide, I just you change slightly the equation by smuggling the 4 into the z times that to the power 3. And then we get this picture. So this looks like a trumpet with 3. So what did Klein do? So he said, I want to classify all the singularities I get in this way. So he says, let's check what are the subgroups of SL2 of C, the finite subgroups. Of course, you can always conjugate them into SU2 of C. I'll just take a, because it's finite, whenever you take an Hermitian product, you can average about it, and then you just take a orthonormal basis for the averaged Hermitian product, and the base change changes G inside SU2 of C. So you can always suppose that it's inside the SU2 of C. But SU2 of C, you can see it as a unit sphere of the quaternions. So it's explained here. So here you have your elements of SU2 of C, and the norm is given here. And so now the map to go to SO3 of R is just you look at the conjugation by X, and this defines an isometry on the pure quaternions. And so you get this map. And so the subgroups of SU2 of C, you'll get them just by pulling back the subgroups, finite subgroups of SO3. And this I just reproduced it because it wasn't the title of Klein's book. It was the icosahedron that was mentioned. And of course, you know that the subgroups, finite subgroups of SO3 are given by the cyclic group, the dihedral group, and then by the symmetry groups of these objects. And so this is all groups you get, and the binary groups are those you get by pullback of these finite groups. And so then Klein observes, whatever you do, in all these cases, you always have 3 invariant polynomials and 1 equation. And so he classifies them. So you have now I have this list of groups, 2 infinite series and 3 exceptional groups, and the equations are given by this. So what I would like to do now is what you do in algebraic geometry if you want to understand the singularity, you deform it. Let's do this by looking at it. I just added a parameter here. It's a little bit tricky to add the parameter in such a way that everything stays real, but you see how it changes. And let's deform the list I've shown you. You see it here. And now that's interesting because it helps to make a difference between this singularity and this. They look a little bit similar if you look at them, but if you deform them, you see how different they are. Same here. So now have a look at the following thing. I have a small loop here, and I have a loop, 2 loops here, and they meet at one point. And I have 3 loops here, and they meet here and here. And here I have 4 loops. So they loop, if I use the diagram where the vertices are the loops and the edges are, if 2 loops meet, you get this diagram, which is written there. You just see it readily by looking at the deformation without doing anything complicated than deforming it and looking at the picture. Let's do this one. So do you see it here? So here you have 4 loops, and they meet following this diagram. So you get another interesting diagram. And so, of course, you can do this for all of them, and what you get is these diagrams. So you get something interesting, because these diagrams, delta G, we know them from the classification of finite dimensional Lie algebras. These are the so-called ADE Lie algebras. And this is why people call these Kleinian singularities very often ADE singularities. And so the type is A, D, E6, E7, and E8. And very often, I just note them like this. And I forget about the group names. I always think about their names coming from Lie algebras. Another way to do something if you're interested in changing your singularity is what we've seen also yesterday, is you do a resolution of singularities. So it's very easy to do this resolution in the case of this singularity, which is an A1 singularity. So you just look at it what it is, and then you see you have a plane conic, which is just given by this equation. You see it here. And then you define by hand another variety, which is inside the product x cross c. And if you project to the first factor, you don't change anything if you're outside 0, but over 0, you just have the P1, which is the plane conic you've seen. So you resolve your singularities. It's an isomorphism outside 0, but over 0, the inverse image is equal to a P1 of C. It's like in the reals, it's a circle, what we have already seen. And in general, so Duval has shown in the 30s that there's always a minimal resolution of singularities. Let's not get too much into that. It means it's a resolution of the type I've shown you there. So if you look at the set, which is called the exceptional set, so this is formed by rational curves, so by P1s, and these P1s intersect. And so what he shows that Duval shows that if ever you have such a singularity, then which admits a resolution of smooth rational which intersect transversally, so there's an additional condition, meaning that the EI square must be -2. I'll go back to it in a second. Then this is Kleinian singularities. So Kleinian singularities is the same thing as Duval singularities in this. So what is important here is to look at the intersection graph. So you look at vertices, are the P1s, which are in the set of, it's a subset, I should be, it's not an, and then you say, put an edge if they intersect, and then the intersection graph is again the same we have seen for the deformations. And so Kleinian singularities, same thing as Duval singularities, same thing as ADE singularities. And what Duval proves is these are -2 curves. And this essentially means if you look at the, so if you look at the canonical divisor, which is defined as lambda square of the dual of the tangent bundle, then the canonical divisor does not see the exceptional curves. So it's a very special situation you have here. It doesn't see it. The reason for this is the following one. So you have a regular 2 form over C2. And this 2 form is invariant under the action of G because it's that determinant is 1 of the elements here. So over the smooth part, this will descend to the smooth part here inside. So you have a form here, and now what you can ask yourself, if I look at this form, of course it is a form inside the desingularization, but the specific fact what happens here, that it extends to a two-form on the desingularization. It's not clear that it should do. The reason is that the canonical divisor doesn't see the exceptional set. And so there's something which is happening here. And so if you can go back, let's have just a small reminder of real symplectic. So there's no curvature, I'm sorry. What we've seen yesterday. So if you have a symplectic manifold, real one is just you have a symplectic form that is closed. And locally, as Paulo explained to us, a symplectic manifold is not very interested because it looks like the Euclidean space. And so these are, but you can do this also in the complex case. So you really take the same definition here, except that the forms are holomorphic forms if you go to the analytic category, but here I'm the algebraic one. So I would say, I say that a symplectic algebraic variety is just a smooth algebraic variety that has such a regular two-form, such a way that the induced form over every fiber is non-degenerate. And then Bouville made the following definition, which is, you can read it if you go back to the Kleinian singularities. By the way, it's the first example he shows once he makes his definition. He says a normal, so I'm really insisting on the fact that it's a normal complex, so singular, maybe singular variety V. So it's said to have symplectic singularity. So if the smooth part is, there we have a symplectic two-form. And if I take a resolution of these singularities, then the pullback over the regular part extends to the whole desingularization. So it's written for any, actually it's enough to prove it for one, so that's standard trick in birational geometry. And some of these resolutions, in general only one, may have an additional feature, namely that the form, I only ask it to extend as a form, extends as a symplectic form. So that's much stronger. And in this case, these resolutions are called symplectic resolutions. And if we look in dimension 2, this is precisely what happens. So we have this xj, and we have this omega, and we can show that it extends as a symplectic form to the whole desingularization. So it is actually, Kleinian singularity is a symplectic singularity. It's equivalent. And so the slogan is ADE singularities equal Kleinian singularities equal Duval singularities equal symplectic singularities. So now you can ask yourself the question, so what are symplectic singularities in higher dimensions? So you start in dimension 4 or in dimension 6. It must always be even dimensional because it's symplectic over the smooth part. And so you look at hypersurfaces inside C5 or inside C7. And I asked, with my favorite collaborator, Manfred Lehn, we asked ourselves this question. And we said we look for hypersurfaces with symplectic singularities. And then we exclude the case where they come from products from lower dimensions. And so we know in dimension 2 we have the Kleinian singularities. And then we said it's very restrictive for a symplectic singularity. There are many, but if they need a little bit of space. So if they need some embedding space. So it's difficult for them to be at the same time a symplectic singularity and being a hypersurface. So we thought initially that the Kleinian singularity is the only thing you can get. So we tried to prove it, and we proved it many times, but without satisfying proof, because at some point Manfred looked at me and he said, peut-être ce n'est pas vrai. So maybe it's wrong. And we were lucky because I had invited Namikawa at that moment to Nantes. He was there for 1 month. And so we found generalizations of Kleinian singularities in dimension 4 and in dimension 6. So I'll show you how to construct these ones. But it is difficult in general to construct them because how do you do? I mean, you need equations, you need to find them somewhere, and you can't do this by looking at subgroups and going to the quotient in higher dimension. It simply doesn't work. And so I will show you the equations in dimension 4 and 6. And of course, let's continue a little bit further. So the question is a slightly sloppy here because one has to make some restrictions in order to get a better grip on the hypersurface we are looking at. But the first thing maybe one can observe is that these symplectic varieties in general, not only hypersurfaces, whatever symplectic variety you give yourself, it has a natural Poisson structure. So that's usual. You, on the sheaf of regular functions, you can define the Poisson bracket just by using the identification of the tangent space with the cotangent space given by the symplectic form. And of course, this only makes sense over the regular part where the variety is smooth. And then you observe that the Jacobi identity you need for a Poisson structure is actually equivalent to say that this omega is closed, which is true by definition. And it turns out, because this is normal, this Poisson structure, which is only defined over the regular part, is actually defined everywhere. So the Poisson structure doesn't care about, I mean, it's defined all the time. You don't need to take resolutions, anything, it's defined over X. So let's make a small technical assumption, meaning that I want this X to have a C star action. Because the reason is that, so I just want a C star action together with one fixed point. So what you do in order to get this, here it is a fine, at least I'm looking at a fine one, and then you can look at the coordinate ring, and what you want a grading of the coordinate ring, and then this is the same thing as giving yourself a C star action, and we call such symplectic varieties together with a C star action that is homogeneous over the regular part. So this means that the action you see here, if you pull back for every t, it's just given by t up to s omega, and it's easy to see that this is a strictly positive weight you get here. This is done in order to get a little bit of rigidity into the whole picture, to get more grip on the equations. So you would look at conical x. It is a mild observation. So first of all, this also introduces, because of the C star action, the fact that the Poisson bracket is homogeneous, and just translate now the weight is negative, is minus s, and you see that the Poisson bracket satisfies this condition. And actually, this assumption is very mild. All known examples are conical, and at least in the affine, it's not whenever you get one, you verify it. Kleinian has conjectured it that every symplectic singularity is formally locally conical. So in the formal neighborhood, it gets conical, and Namikawa Odaka have proved this in many important cases last year. Also another interesting feature of conical symplectic varieties is that, of course, you can always find minimal homogeneous generators of your ring of coordinates over X, and then let's call AI the weights of these coordinates, homogeneous generators, and you can always put them in the right order so that these weights are decreasing. And and you can always suppose that the GCD is equal to 1, and then this A0 to AN is uniquely determined by the graded algebra R. And so we have a maximal weight. And if you fix the degree, and if you fix the dimension, sorry, and if you fix the maximal weight, then there are only finitely many conical symplectic. So that's interesting. It's a classification question you ask yourself. You fix the dimension and you fix the weight, the maximal weight you get, then there are only finitely many symplectic varieties you can find. Of course, you need this n here because already we have seen, if you look at the Kleinian singularities of type A2n-1, if you look carefully, what are the weights that are in Klein's work? So you see they have weights n and 1. So this, or dn plus 1 have maximal weight n. So if you don't fix the weight, then you get infinite series. So you need to fix the weight in order to get a finite number. And so the overall question is, can we classify them? We are very far away because even for except for dimension 2, we can't do it. So for dimension 2, you may ask yourself, so what are the weights that can come up? And this is easy to show. Yamagishi is a student of Namikawa. Namikawa have computed all possible degrees and weights you can get. So we asked ourselves, this is an invitation. So are there others? Maybe not, but we don't know the answer. So we know it in dimension 2. This is Klein, and Yamagishi has proven it in dimension 4. But even in dimension 6, we don't know how to prove that. So, and we suspect that in dimension 8, there's no one. We suspect, but we don't know. Peut-être ce n'est pas vrai. Because we only have one way of constructing hypersurfaces. I will show you the way. Maybe there are other ways, and maybe we miss simply something. So there's maybe no reason that this invitation is a correct invitation. So I don't say it is a question. Let's say it's a conjecture. So let me just quickly explain to you how you can get these new Kleinian singularities in dimension 4 and dimension 6. The idea is to go back to a theorem by Brieskorn that had been conjectured by Grothendieck in the 60s. So we go back to the deformations. As you've seen, that was interesting to deform because we saw many things when we deformed it. So Grothendieck said that if you look at the adjoint quotient map of a simple Lie algebra, then for specific cases, this should provide these deformations semi-universally. This is the best you can expect. And so this has been proved. Another ICM had been shown in the 1970s in Nice. And so let me just explain to you what is this adjoint quotient action. So let's think about SLN of C and the Lie algebra, which is SLN of C. And then G acts on its Lie algebra by the adjoint action. And you take the quotient in the sense of invariant theory I've shown you already. And so if you take an element of X, then you always have this decomposition into its semi-simple and nilpotent part. And so this map is just given by the semi-simple part of your element of your Lie algebra. Then you do very classical thing, take the Cartan subalgebra, look at its Weyl group, and by Chevalier you know that this quotient is actually the same as taking this quotient here. And if you look over the fiber over 0, what you get is all nilpotent elements. Let's look at, in the case of SLN, this of course, you do all the time. Your application is just, you take your X and you send it to the set of its eigenvalues without specifying the order. That's the map. So that's the adjoint quotient map. And so we are interested in the nilpotent cone. This is nilpotent matrices. They have this Jordan block decomposition. And then you see that this decomposition, they are just given by the partition. And so you see that there are specific orbit under the, there's an action by just conjugating these matrices, of course. And then you have a special orbit. And the one which is called the regular one is the dense one, where the partition is just n. And then you have in codimension 2, you have a big block and a small one. And then the minimal orbit you can get is there where you only have small blocks and 1, 2 block. And then, of course, you can always have the 0 as another one. And so what people do, and what Slodovy did, Slodovy is a student of Briscoe. He said, let's look at an element X, which is nilpotent. Let's look at its orbit. And then there's an SL2, which is naturally existent. Here, you can always find another nilpotent element and a semi-simple element that you have an SL2 triple inside. And then you can look at the adjoint maps to get a slice here, S, which is a slice inside G. And so this one is transversal. And this transversal slice, if you intersect it with the nilpotent orbit, then you get what is called a Slodovy slice. And if you look at SL2, so then the nilpotent orbit is just given by this equation, of course. And we only have 2 orbits, the regular one, which is the minimal one. And so the element x equal to 0 is in this subregular or minimal subregular orbit. And then S is SL2 of C. But if you intersect it with N, then S0 is just an AI singularity. So you get your A1 singularity just in the simplest case. And you can do this resolution type simultaneously. And you get a simultaneous resolution of the Slodovy slices. I go slightly faster because I want to say something else afterwards. And then the main result is, if you look at the subregular orbit, so subregular orbit means that the slice is of dimension 2. So we are in the Kleinian case in dimension 2. Then Grothendieck and Briscoe-Slodovy's theorem is to say the following, is to say that S0 for this specific subregular orbit, S0 is a surface and it has exactly one Kleinian singularity at the nilpotent element X you're starting with. And the resolution, which is a universal resolution, is actually the minimal resolution, has been proved by Steinberg and Titz and Inu a little bit later. And then if you look at the singularity type, it pretty much depends on the Lie algebra you're starting with. So you see something interesting happen here. So here you have all simple Lie algebras, but the singularity type is only of ADE type. It can't be differently because Kleinian singularities are ADE singularities. So Slodovy classifies all them. But for us, it is interesting to do the following, is to look, that was the idea we had at that moment, was to look at other nilpotent elements because we wanted higher dimensional analogues. So subregular gave slices of dimension 2, but if you look at orbits which are lower dimensional, then the slices get higher dimensional. And so we expected that there must be also some deformation theory that we could track. And difficulty here is that in these cases, these slices do not have isolated singularities anymore, so you can't use usual deformation theory. And but we observed that it is a Poisson structure, and then you can do something which is called Poisson deformation, which you can define in an abstract way. And the theorem we proved together with Yoshinori at that moment and Manfred was it was the following one: if we take a non-regular nilpotent element, then so we are not precisely not in the case where the slice is of dimension 2, but so actually it includes also, but we are interested in the part where it's also of lower codimension. Then we see that the formal universal Poisson deformation exists only in very specific cases. So these are elements which are not of ADE type. Something specific happens here. Let's not go too much into it, but for ADE Lie algebras, which are simply laced, then we always get the Poisson deformation, so we are always in the good deformation case, as we have seen in my films in the beginning. And so there's some technical remark related to the fact how this is proved. We proved this isomorphisms had been proved at the same time by Braverman, Maulik, and Kunkel, but with another way. And so what we get is 2 in dimension 4. We look at this specific Lie algebra, and then we get this equation, which is a Kleinian singularity in dimension 4. So we were very happy when we've seen this equation. And then we looked at all other orbits where something could happen, and we figured out that in dimension 6, if we look at the Lie algebra G2, so there are 5 nilpotent orbits, so of dimension 12, 10, 8, 6, and 0. But the minimal orbit of dimension 6, there is a universal Poisson deformation, and then you can show that you get a complicated hypersurface, and it's a symplectic singularities. So that's the only way how we know how to produce concretely equations. So these equations are, and we show that no other one gives a hypersurface. So there's no way to get another Kleinian singularity using this method, but maybe there are others. So so it's a classification problem. Yesterday we were told that compact is also interested. Compact has a very similar flavor. You look at, let's go to the holomorphic symplectic setup. So you just ask for compact Kähler, simply connected manifold. Now this thing doesn't work anymore, but so then you can define holomorphic symplectic manifold. It's the same definition, just we look at in the holomorphic setup. And so there's same question, which comes up if you ever take a compact Kähler manifold which has trivial first Chern class, then there are exactly 3 types of varieties you can get. So either complex tori, either holomorphic symplectic manifolds, or Calabi-Yau manifolds. And so these holomorphic symplectic manifolds are building blocks for manifolds with trivial canonical bundles. And so one case in dimension 2, so which is the symplectic manifolds in dimension 2, these are what are called the K3 surfaces. So typically it's a hypersurface of degree 4 in P3 of C. I've made a small picture here again. And so it's named after Kummer, Kähler, and Kodaira, et la belle montagne K2. André Weil gave this naming. And so the question came up, are there any of higher dimension larger or equal to 4? And actually there are, but only 2 in finite series. So the one is, we more or less have seen it yesterday as well. So we look at the complex surface and consider its product with itself, and we let act the symmetric group of R elements just by permutation on these things. And then we take the quotient. So this will be singular again, but it has a natural desingularization, which is what is called the Hilbert scheme of points on a surface. It's just the length R subschemes of S. And if you send the subscheme to its support with these multiplicities, so then you get this desingularization, which is written there. And then you have two infinite series and two isolated examples in dimension 6 and 10, and that's it. Here again, many constructions have been done by many people in order to find other symplectic compact manifolds, but so long list, I won't read it, but whenever we did a construction, it deforms to one of the known examples. So here again, we are living with this difficulty that the symplectic manifolds are somehow rare, even in the compact setting. So you can have a look at the whole situation is a little bit here. So O'Grady 10 and O'Grady 6 are two exceptional symplectic compact manifolds. They are constructed using singular moduli spaces of sheaves over K3 surfaces or over an abelian one, and then by constructing a symplectic resolution of these symplectic singularities. So they come as symplectic resolutions pretty much the same way. So this is where we are standing. So nothing more to say, except that we don't know how to construct others. And people say the lists are complete. Others say, why should this list be complete? There's no reason for them to be complete. So after, when some time ago, when I was listening to this talk by Jordi, we've seen, I think, in Sydney. So he showed us some combinatorial problem where he used some classifiers, some neuronal networks to classify things. So I played around with this with equations. Of course, the compact case, I can't do anything, but with the equations, you can actually play around. It's funny, it's fun to do. And so you can start in dimension 2. Of course, you can, what do these neural networks do best? They can classify things. So at least they started like this. Typically, if you have a car in a photo, that was the very, very, very first beginning. These were much better to see that there's a car in the photo because they get trained by many, many, many images where a car is in the photo, and whereas normally you would use the theory of shapes, trying to find out whether there is some part of what could be a car inside the photo. That's technically difficult, but these neural networks work much faster in order to identify and to classify objects in an image. I think it started like this. So you can do this with equation the same way. Of course, it doesn't work that well, because if you do it with brute force, equations have coefficients, and coefficients are many, and it's a too big problem to do. But you can do something which what I call a neurosymbolic workflow. So I introduce some mathematics into these neural networks because just doing raw coefficients is not working. And so the reason is not to use a pure thing. Is, of course, I tried the pure one, the program. It's not difficult to do nowadays. and you can download some verifiers, and not too difficult to do, and but it didn't work at all. So you need to input some mathematics. This is why I say neuro-symbolic workflows, because the mathematical constraints are very rigid in dimension 2, and already, and we know in dimension 2, 4, and at least we have an example in so we combined learning with symbolic verification. So I implemented some Python scripts, and so I have a verifier which is fast and detects in dimension 2 at least, and it detects the families we know. So this is training. It doesn't take long, even on a laptop, to get a lot of cases, but it's not strong enough. So I use in dimension 2 these Jacobian Hilbert functions. This gives a footprint of your singularity, and then it's much easier to check if you have an equation whether it satisfies the footprint or not. And so you can train and you can let it work, and you can let it work, and it works and it works. But the unfortunate thing is that if you want to do the stronger checks, so I use Macaulay too, because this is the one I know, but you can also use singular, but it always called singular, and it takes time, because these algebraic verifications are long, much longer as you would like to have if you want to train things. So you can do. There's dimension 4 and 6. There's an additional algebraic obstruction, which I call the Poisson-Pfaffian reconstruction from the gradient of f. And this one is also easy to compute, but it always takes a little bit of time. But you can get some positives from the theory, and then you can do some augmentation. So meaning you get more examples, and you create more examples. And then of course, you can easily check whether one is not a symplectic singularities. Just for instance, you have different zero sets which you would not expect, and you get some big data set, and you train, and then you wait. And I use this thing called p-torch, which is very common nowadays to do that. And then I got equations in dimension 6. And so there's a little bit of the mathematical content. And then I checked. So it checks, it does everything well until dimension 6, so all cases, because there you can change the equation, and it's still a Kleinian singularity. I mean, I took generators and relations of the invariant algebra, but you can take other generators, then you get another relation, meaning another equation. So there are many different equations. So it needs, for the training, you need to ensure that it does. And so this works well. It really works amazingly well. But then I got some equations, and then it took me a long time to check that all the equations this thing got were not symplectic singularities in dimension 6, because it's not always easy to check that. So I did not find a new example in dimension 6. I was pretty much confident, but for the moment, I do not have anything. So I tried in dimension 8, but then the number of variables, so I need a bigger computer then in order to get something. But at least it's an interesting try to get another way of looking at equations with the more modern way, where you don't use any mathematics except this verifier thing, which uses very basic mathematical input. Okay, thank you.